Most product engineers think warranty issues are a customer service problem, something you deal with after products fail. That's completely backwards. Warranty failures are actually created during the design. When you choose materials, when you define tolerances, when you specify assembly methods, those engineering decisions determine whether your product runs reliably for years or starts generating expensive warranty claims. I'm Adam Taven. After developing over 2,000 products, I could look at a set of engineering specifications and immediately predict which ones will create reliability problems. The difference between products that last and products that fail comes down to decisions made during the design, not customer service policies. Today, I'm going to show you how experienced engineers can eliminate warranty disasters before manufacturing even begins. Point 1. The engineering decisions that create warranty claims. Let's start with the design choices that quietly create future failures. First, material selection. Choose the wrong plastic grade, and after 18 months of UV exposure, your product becomes brittle. Cracks start appearing. Second, tolerances. Loose tolerances create vibration gaps. Tight tolerances create thermal expansion problems. Both lead to failure. Next, joint selection. Snap fits feel great in prototypes, but repeated use causes fatigue. Threaded connections with proper design, they maintain integrity for years. Surface treatments matter too. Skip corrosion protection and metal parts rust. Choose the wrong coating, it peels or wears through. Fastener choices are another trap. Use standard screws in high vibration applications. They loosen. Specify thread locking compounds. Connections stay secure. Assembly methods also determine reliability. Complex sequences create opportunities for worker errors. Simple assembly processes create consistency. Even component placement matters. Put stress-sensitive parts in high-load zones, and they crack first. Design around stress concentrations. Products last longer. Every one of these decisions gets locked into your design, and every one determines your warranty rate. Point 2. Why reliability testing prevents field failures. Experienced engineers don't guess about durability. They test for it. Stress analysis reveals where products will break before customers ever see them. Low concentration points get redesigned early. Material testing catches compatibility issues, chemical reactions, environmental exposure. Better to discover them in the lab than through product returns. Environmental validation matters too. Customers don't use products in controlled labs. They use them in heat, cold, humidity. Testing across real-world conditions prevents surprises later. Fatigue testing predicts lifespan. How many cycles can your hinge survive? 10,000? 50,000? Without testing, you're guessing. Vibration analysis identifies loose connections. Shake test assemblies now, or discover rattles after shipping thousands of units. Thermal cycling shows how materials expand and contract. Interference fits that look perfect at room temperature may fail in real-world temperature swings. Accelerated aging compresses years into weeks. Engineers simulate long-term exposure, while fixes are still affordable. Because finding failures early is infinitely cheaper than discovering them through warranty claims. If you're wondering whether your design accounts for these reliability factors, you're not alone. Most inventors focus on functionality and overlook long-term performance. I offer free strategy sessions where we can talk through these reliability considerations with your specific product. We'll identify which design decisions might create warranty issues and how to address them before manufacturing. Click the link below to connect with our team. Point 3. Manufacturing specifications that control reliability. Design decisions alone aren't enough. Manufacturing specifications determine whether every unit performs the same. Process controls ensure consistency. Factories need exact instructions on how parts should be made. Without them, quality varies. Inspection standards matter too. Define which measurements must be checked. Otherwise, defects slip through. Material requirements are critical. If you don't specify exact grades, suppliers may substitute cheaper materials. Assembly procedures also control reliability. Specify torque values and workers apply proper preload. Leave it to judgment, connections fail randomly. Quality checkpoints should exist throughout production, not just at final inspection. Supplier standards are equally important. Qualified vendors produce consistent components. Unqualified suppliers introduce variability. And documentation deserves knowledge. Written processes ensure quality survives shift changes, personal turnover, and factory transitions. Reliability isn't accidental. Point 4. How senior engineers design reliably from day one. The best products don't just work. They're engineered for long-term performance. Design for manufacturing analysis happens early, during concept development. This eliminates failure modes before detailed engineering begins. Component standardization also helps. Fewer unique parts means fewer failure points. It also simplifies replacement inventory. Redundancy planning protects critical functions. If one component fails, the product continues operating. Maintenance access is another key principle. Serviceable parts should be reachable, not buried inside assemblies that require full disassembly. Modular design enables targeted replacement. Customers can swap worn components instead of discarding the entire product. Material selection should match real-world use, not just minimize cost. And systematic failure analysis examines every potential weakness. Engineers ask, what could fail? Then they design solutions before building anything. This is how reliability becomes part of the product, not something you hope for later. Warranty costs don't begin in customer service. They begin in engineering. Material choices, tolerance decisions, assembly methods all determine whether your product performs reliably or generates endless warranty claims. Most inventors prove their concept works, but they never validate whether it keeps working. Successful products aren't just functional prototypes. They're reliability engineer systems. Your prototype proves feasibility. Reliability engineering ensures sustainable success. Understanding reliability engineering principles is one thing. Applying them to your product is another. Every design has unique failure modes and performance challenges. At Rabbit, our engineering team performs these reliability evaluations as part of our development process. We identify potential failure points, validate performance requirements, and engineer long-term reliability before manufacturing begins. If you'd like to see how these principles apply to your product, click the link below to connect with our team. If you want to see another critical engineering decision that affects product success, watch my next video, Why Most Product Prototypes Fail Before They Ever Launch. It shows you the validation steps that prevent expensive development mistakes. So click the link now.